Welcome everyone. Today we're going to talk about our new Mars mission, the Mars 2020 rover, and some ideas we had for doing onboard scheduling. So we'll give you a little introduction, and basically we're going to take a top-down tour of some ideas we had kind of at a system level. This is very early, but we're going to walk through what we want to do on board as far as autonomy for this mission. And I want to give a big thank you to, this is a team effort on these ideas. Stephen Kuhn's our system engineer, and he's come up with a lot of this and negotiated together. Also a huge thanks to Steve Chen, who's here. They have a tremendous amount of experience, and his wisdom and inputs have been really valued. And also to his whole team, especially Greg Rabideau. He's actually joining our software development team, and he brings with him quite a bit of experience as well. So thanks to all of those folks. So this is the Mars 2020 rover. It might look familiar. This is, the body is essentially quite similar to the Curiosity rover, which is on Mars now. A lot of it's going to be very similar, new instrument suite. And it has a bit different goals. This one's going to collect core samples from rocks, hopefully leave them on Mars for maybe pick up by a future mission. But it's going to leverage quite a bit from the Curiosity mission, both in terms of hardware and in terms of software. So we have high hopes for a decent amount of reuse and refactoring on the 2020 mission. Let me introduce to you some of the terms I'm going to use in this presentation. A sequence is how we do commanding traditionally. It's a file consisting of essentially time-ordered commands. And on Mars missions, and particularly on Curiosity in 2020, we need to put the rover to sleep at night to recharge the batteries. So it has that sleep-awake cycle, which is a bit unique. Some of the orbiters don't have to deal with that. In addition, before we use an actuator, perhaps we need to heat it up in advance so it's nice and toasty and safe to use. So we will talk about preheating in this presentation. And also we have this term called a parameter, which is essentially a saved value on board the spacecraft. It's really only changeable by the ground. So let me introduce you a little bit to the prior process that was used on the Curiosity rover. Any action, again, was started up by a series of sequences, typically. The ground has to create these sequences maybe every day during the work week, say, or every other day. And the process is quite lengthy, right? To go from data coming down from Mars to actually creating the sequences, analyzing it, testing it, putting it all together, doing safety checks, that can take over 9 hours. Not always, but sometimes. Also, due to uncertainty in terms of how long a particular sequence might run, or just the onboard behavior, margin has to be inserted into these sequences, and that does result in some cases, wasted time, wasted onboard energy. Also, because the ground has to be in the loop for this sequencing, you really can't take advantage of the onboard knowledge. Suppose a sequence finished early, right? We might take advantage of that extra time again. So that's another something we would like to improve upon. And also the operation team just has to manage sleep activities and preheat activities. Now there are tools on the ground to assist with this, but again, that is still part of the process that has to be taken care of on the ground. So we wanted to do some improvements for the mission, the 2020 mission. Several goals. One is to improve operations efficiency. If we can run more activities on board, that's a great help. Get more science done. We can have less wasted less wasted resources in terms of time and energy. And another driving factor is, instead of taking 9 hours, we want to enable the ground team to be able to generate their uplink products within 5 hours, right? And if you have a shorter time to create these products, that allows you to get more done on board more often, have more useful days of rover productivity. And so to accomplish that, the vision is that we have this onboard piece of software. It's called the onboard planner. It's really more of a scheduler, though. And what is our goals for it is to run more activities when more power is available, start activities sooner if the current activity finishes early, and also onboard manage the sleep cycle. Have onboard the rover decide when to go to sleep. And I should let you know this is very early work. We're just starting the prototype. We're just getting early versions of sort of essentially systems desirements. So what I wanted to do is kind of share with you where we are now. Top-down approach at a high level, sort of giving you a vision of where we want to go, what are the basic capabilities, what does the ground need to tell the spacecraft, and just kind of give you some ideas on the architecture. So we're not going to be talking about implementation today. So at a high level, what does the planner do? The planner is going to be responsible for scheduling all the onboard execution on the surface of Mars. So to take you through that, it all starts with the operations team, and they're going to create a plan file using ground tools, various techniques, and that file is then going to get uploaded to the onboard planner on the spacecraft. And what the onboard planner is going to do, first of all, it needs to make predictions into the future about the state of the spacecraft as far as various resources, for example, power or data volume. You can think of others. We'll talk about others. And once it makes that prediction, given the knowledge of what constraints there are, what resources are going to be consumed by various activities, and a lot of that comes from the ground. Oops, sorry. A lot of that comes from the ground. Based on all those inputs, both the ground plan file and predictions, it's going to generate a schedule on what activities can run when. And this is the onboard portion right here. And in doing so, it's got to, as I said, make predictions and check for conflicts. Okay, so the plan is contained in a plan file that is what is uplinked from the ground. And so what we're going to do is we're going to decompose what is in the plan file into various capabilities and data and kind of break it up. So that's going to be the rest of this presentation. It's starting at the high level. What is a plan? What is inside a plan? And how do we use that information on board? Okay, so as I said at the top level, the plan file is what is uplinked from the ground. Inside the plan are activities. So an activity is the lowest level that the scheduler is going to look at. So it's something that can get moved around and executed at a certain point in time. It's that level of granularity. So that's an activity. And as I go through the presentation, we're going to talk about the various types of activities. We're going to talk about various constraints on activities. So we'll go through that in detail as we walk through it. Now, I should also define the term handover. Handover is a point in time when we move from one plan to another. And that's very common in rover operations. In the past, it was, say the rover has a wake-sleep cycle for one day, and then at the end of the day, it's going to hand over and start executing the next day. So it's sort of handing over from one day to the next what the rover is going to do. Okay, and that's a specific point in time. Now, what we have is certain goals that must be achieved at that point in time that we hand over to the next day. So for example, we want to provide the next day with a minimum state of charge so they have enough energy to do their rover activities. So that's sort of one goal. Additionally, we only want to generate a certain amount of data within, say, one day. So that's another data that the ground provides, is a limit on how much data we will allow to be collected. We have an end time, And we also have the name of the next plan file, so you can kind of chain them together one after the other. Okay, we're going to walk through this in a bit more detail, but I wanted to start giving you sort of the UML big picture of what we have. So at the top is the plan. It consists of a bunch of activities, and the activity itself contains a bunch of constraints. And we'll walk through this in greater detail as we go. Okay, so you got the big picture. Now I'm going to look at activities. There are various types of activities. Some of them behave different from each other. We're going to walk through that. So as I said before, the activity is the item that is scheduled. It has a type. We're going to go over the types. Each activity has a unique ID across the mission, and that'll come down to telemetry, and it'll make it easier for us to understand what's happening on board. Each activity is going to kick off a sequence, so that's leveraging the legacy system for actually doing the low-level command execution. Each activity has a priority, and we'll use that to categorize activities as mandatory once they're intended to execute for sure, and optional activities are ones that are sort of nice to have. Execute it if you have more resources available. That's kind of the high-level intent. Okay, so activity types. The most common would be just your generic activity. It runs a sequence, and it has a fixed duration, and that would be the vast majority of what activities we use. And then we have some more specialized ones. An expanding activity is essentially the same as generic activity, but it does not have a fixed duration. It can potentially grow in how long it executes. One typical example would be a drive, right? We might say, go ahead and drive until we run out of meet the power constraint, say. And we don't know how long that's going to be, but just keep going. And so that's the use for an expanding type activity. Now, there are a case, say for an instrument, where they have an activity that's very resource intensive. And if it so happens that we don't have enough resources on board to execute it, we'd like to do a backup plan. We'd like to do something similar but less, that consumes less resources. But the key constraint is we don't want to execute both of them. You want to do at most one of activities on a list. And so that's where these single selection groups come in. You just choose one from the list, one that fits. But you cannot run more than one on this list. So that's the intent there. For the stay awake activity, that's just a way for the ground to force the planner to make the spacecraft be awake for a certain period of time. Because as you remember, the planner can autonomously generate sleeps. So it's just an enforcement. The ground taking some more control back in a way. We also have several types of shutdown-related activities. As I mentioned before, the planner can autonomously generate shutdowns. And we also have the capability to have manually described shutdowns on the ground. Now, because we are tracking resources, there are different sets of resources that are consumed sort of during the different phases. So when we're actually sleeping, there's one set of resources consumed. During the actual shutdown, right, the various resources consumed would be different. Here we'd be gaining energy, here we'd be losing energy. Similar for as we're waking up, we're actually going to model the energy and data volume that it takes to actually wake up, come out of the sleep. So that's how we break it up as far as those activities. We also have the notion of comm windows. These are periods of time during which the rover is going to be communicating with Earth. And so those are sort of a special case. We have onboard software that already manages that. And so the planner is going to need to be aware of the comm windows and sort of manage its schedule around them. And so that's something that we explicitly need to take care of. Okay, so those are the types of activities. Now we're going to look at attributes of activities themselves. So these activities, its duration, how much energy it's going to use, how much peak power it could take up potentially, how much data volume it's going to generate, the number of sequences that it could potentially spawn at the same time. Those are all modeled by the ground, and those are uplinked as part of the plan file. And we need that to do our onboard predictions and modeling and check for conflicts. Additionally, we need to tell the scheduler when can an activity possibly run. And we can constrain that. We can give it various constraints on the start time. We can say, let's start between 10 and 11 or between 1 and 2, something like that. So we can have multiple start time ranges. We also have a cutoff time as well. Okay, dependencies. One activity can depend on another. And so we allow expressing that dependency. We can say, B depends on A successfully completing. And we can also check on other status of the activity, whether it's completed, whether it failed, whether it succeeded, whether it was aborted. Okay. So those are dependencies. We also want to constrain parallelism. For example, on a rover, if you're moving the arm around trying to pick up a rock, you probably don't want to be driving around at the same time. That would be a bad thing. So what we want to do is sort of tell the planner not to schedule certain activities in parallel. And the way we're going to express that is just to have a bunch of bits dedicated for each activity. And we'll let the ground define how these bits are used. But basically, if the same bit is set on 2 activities, they're not allowed to run in parallel. The scheduler will make sure that they do not run in parallel, which is what I'm showing here. These 2 activities have the same bit set. And so because of that, this sort of schedule would be forbidden, and this one would be allowed, where they're not running in parallel. We talked about preheating earlier in defining terms. So again, we need to warm up an actuator so it's nice and toasty when we use it. So the way we model this is each activity essentially is a checklist of what thermal zones that it will use. And that's all the ground has to specify. And then we need to do some more work on board. As we place the activity, right, as we put it on the schedule, we have to schedule both the activity as well as the preheat. And also, as is a new sort of requirement for flight software, it's responsible for generating and executing the preheat, monitoring that it's running successfully so that we're at the correct temperature before we run an activity. So that's an interesting new capability. We also have some checks that are done onboard against onboard variables. Just some terms, ACM is a saved onboard variable, typically allowing or precluding a particular action. For example, if there's a problem with the wheels, then we're not going to allow a drive. DDI is basically it's something that doesn't persist across a reboot. It's just an onboard variable. And so these can be evaluated and used to determine whether or not we can start a given activity. It's a constraint on the activity, essentially. And at this point, right, because they're onboard values, they're essentially onboard variables, right? We're not exactly able to predict them, so they have to sort of be evaluated as you're sort of dispatching the activity. Okay, so more features. We're going to talk about some of the overall constraints. Now that you've seen what a plan is, what an activity is, what data is inside activity, now we're going to talk a little about some features and how we use those constraints to sort of do modeling of predictions in the future. So as far as limiting the data storage, right, we don't want to allow the planner to fill up the whole hard drive, essentially, right? We want to constrain that. And so the way we're doing that is we're going to look at the delta data volume that is generated, right? And so that we know from the ground how much each activity is going to generate. And so basically we have some limit, right? And we check all the activities that we're trying to schedule, and we check that against the limit. Now, there's some distinction between a mandatory activity and an optional activity. We're going to be less conservative on the mandatory activities. Mandatory or in ground intent, they really want them to run. And so we're going to let them go over the data limit. That's okay. Optional activities, which are the nice to have activities, those ones we're not even going to bother scheduling if they would violate the data storage limit. And this is all limits on sort of our flight computer. We're not talking about data stored on the instrument. That's going to be outside of our scope. Okay, now we're going to talk about state of charge. So for each activity, we're going to know how much energy it's going to consume, and we know its duration. And for activities that are generated on board, like sleeps, for example, we're going to be able to get that same information as well from parameters. And so these are basically the inputs we need. We need how much the activities are going to consume. We need how much is going to get consumed in a quiescent state. And so given that and actual readings from the hardware, we can get out estimates of how much energy is going to be consumed. We can get an onboard estimate of the available capacity, and from that we can predict the state of charge. And so we'll have various constraints on what the state of charge can be, both at the end of the plan and sort of an overall minimum that you don't want to dip your power below. We also have a constraint on sort of the amount of the peak power that can be like a spike at one moment in time where all the activities collude to give you just a worst case spike in power. So we want to avoid that. And so we can track that. There's an attribute that comes from the ground giving us peak power for each activity. And so if we add those all up at a given moment in time, we would know if we exceed a given threshold there. So we have, as I said before, we have our estimate of the current state of charge. We can predict state of charge. So now we want to check that against certain limits. There is one limit against which we will not schedule an activity. That's the soft minimum state of charge. Now, if we're already executing, we can violate this soft limit. It's used to as part of the scheduling. We're scheduling against the soft limit. Now, once you're running, though, there's a second limit that's a bit lower. That would be the hard state of charge limit. And if we find an activity that's actually running, and that actually we have violated the state of charge limit, then we're going to take some action against those activities. So we're starting to get more and more drastic. Additionally, there's a constraint. Again, this one is a looser one that's on the state of charge at the end of the plan at handover. Optional activities, which are the nice to have ones, we're going to check against that. Again, here, mandatory, trying to honor the ground's intent, we're going to let those slide even if they would violate the state of charge at the end of the plan. Okay, so on board, we're going to need to initiate sleeps, shutdowns. Some of that is going to be driven by parameters that limit, very short sleeps or very short awake periods. Additionally, right, we want to try to run activities, right? So we don't want to be sleeping all the time. So if a mandatory activity could be scheduled without violating any constraints, we're going to schedule that in favor instead of a sleep. Same thing, if we could get optional activities in there without violating its constraints, we're going to schedule that optional activity. And only in those other cases where we can't do anything else unless we could go to sleep, then we're going to do the sleep. There's also some constraints on sleeping too much. We don't want to remain at a very high state of charge all the time. Apparently that's bad for battery life, so we're even going to take that into account and try not to sleep too much. That's going to be parameterized. In fact, in the case of an activity failing or getting aborted, we also have these special activities called cleanup activities that establish a known state, and they're just going to run a sequence, do the cleanup. This is an off-nominal thing, but it is taken into account as we establish our planner architecture. An abort, okay. So this is where the planner actively stops a running activity. So not only is it scheduling, but it actually has a monitoring function as well. And if activity is overrun, its cutoff time, it's going to get aborted. If it's running and we hit that hard stated charge limit, it's going to get aborted. Optional activities, again, these were the nice to have ones, we're going to be particularly strict against them. So if they run over their duration, they get cut off. And typically the effect of an abort, we're changing the activity state, stopping it running, and then most likely the planner is going to run a cleanup activity after the abort. So conclusion here, I think I've showed you some of the features that we want to do. For the 2020 rover, we want to increase autonomy. We want to do the onboard scheduling that I've described. In particular, some new capabilities are the onboard power estimation, onboard sleeping, doing the preheating. We discussed constraints that the planner is going to have to manage as it's doing its schedule. We've showed an enabling set of knowledge, right? So a lot of this knowledge has to come from the ground. The ground has to tell the planner what does an activity consist of, what resources is it going to consume, what are the constraints. So there's a lot still of knowledge that has to be uplinked. Still, on the whole, we hope that this improves the mission, and we really want to enable more science, right? So more activities running on board, utilizing those extra onboard resources that we really couldn't do on MSL if there was extra time available, if there was extra energy available. Let's run some nice to have activities that the ground provided us. And let's try to reduce the workload of the ops team so they can actually get done in 5 hours. We're helping out with that with autonomous sleeps and preheats, reducing some of their workload. And as I say, this is all so far very early prototyping, so we're kind of just discussing the architecture. But future work, we're going to continue our prototyping and development, and one of the early things we want to find out is from our prototype, let's find out the RAM and the CPU usage, and that will help guide our further implementation and further design decisions. All right, that's what I have, and I'm happy to take questions.
Hold on, let me get a microphone so people online. Or not. Okay. What do you think? Give it a try.
Yes, test. No?
Nope.
Okay. So what jumps out is that the planning of activities seems to become an optimization problem. So have you guys thought about, like, is there a specific solver or solution that you're going to implement, right? Because if you have multiple optional activities, for instance, well, maybe 2 of them cuts off the end state of charge, but maybe
Sure.
you can actually get 3 different ones in instead, right?
Repeat the question.
So the question is, have we chosen a solver, say, or are there lots of... And the answer is, well, first, we're early in prototyping. I will say, though, that this is real time. And so we're very much not trying to do something that is optimal. We are trying to do something that would fit in our available onboard resources, which is a very slow processor with very little RAM. And so to me, it's more important to be timely and correct. So I want to make sure that all plans and schedules we execute are safe. They may not be the best one, but they cannot violate the constraints, and I think that's the most important thing. And then everything after that is sort of, yes, maybe we can do some more in terms of, improving performance, but I would never use the term optimal for sure.
But if that being the case, then it seems to diminish the value of this, right? Because then it's just going to basically execute what you would have already told it to execute.
Well, I think the advantage is that what it does is it takes advantage of onboard knowledge that the ground couldn't possibly have, such as, I finished early, I have more energy. And so there's a chance that it can fit more in there. So it might fit in something, but that might not fit in the best.
Okay, so it's more like a simple sequence logic
Yeah.
date.
Right. Right. It's definitely not a planner in the planner sense. It's, yeah. There's one in the.
So I have a question about the relationship between activities and sequences. So taking a picture is something you do all the time, but where you're pointed may be different. So is the sequence uploaded specifically for the activity, or is it a canned sequence
Right.
where the activity is passing parameters?
Right. So the question is, are the sequences sort of canned, or are they specific to that particular day's objective? So let me tell you what we do on the legacy system first. So typically on the legacy system, most sequences are customized and re-uploaded each time. There is certain ones that we can reuse, but for the specific day-to-day things, it's not just changing an argument here or there. It's actually a new sequence. So that was true even in the legacy system, and we anticipate that will continue. That there would be what we upload would be sort of fresh each day. Now, having said that, there's all sorts of ways you can use tools on the ground to help you out, so that it's not perhaps handwritten every single time, right? So we'd probably, the more that you're talking sort of about it like a template, and that sort of thing, we would do some on the ground, some in flight, but typically sort of a new upload every day sort of thing.
What language you're using and why did you choose it?
So the Mars 2020 rover is highly inherited in terms of hardware and software from Curiosity. Curiosity is written in C. Most of our flight projects are written in C with a tiny bit of C++. And so we're continuing, because of largely the inheritance story, to go with C.
Okay, we got time for one more question. Hold on. Wait. This might work.
I was just wondering, are you leveraging Casper for like your planner logic, or where's your baseline coming from?
So not supposed to talk about implementation too much for ITAR reasons.
Don't worry about it.
But I will say we have Greg Rabideau on our team. He has a lot of experience with planners, and he's a great guy, so glad to have him aboard.
Okay. Very good. I think if there are more questions, capture Eddie in the hallway. It's 10 o'clock. Thank you, Eddie.
Sure.